If you look up at the night sky from the southern hemisphere, you'll spot these two sort of hazy-looking clouds. They've fascinated observers for ages.
A Magellanic Clouds.
Exactly. Named after Magellan, of course, tying back to those early European voyages. Makes you think, doesn't it? How long we've been staring up at these neighbors.
I'm wondering what they are.
Precisely. And that's what we're diving into today. We really want to understand these nearby galaxies, especially with all the new data, particularly from the Gaia mission. We're drawing heavily on this fantastic source, Perryman Gaia 038.pdf.
Right, and they're not just faint smudges. They are proper galaxies, just, well, smaller than our Milky Way.
How much smaller are we talking? Give us a sense of scale.
Okay, so our Milky Way is huge, about 100,000 light years across. The Large Magellanic Cloud, the LMC, that's the bigger one.
Hmm.
It's maybe 14,000 light years wide, and it sits about 160,000 light years away from us.
Okay, 160,000 light years. Still incredibly far. And the small one.
The Small Magellanic Cloud, the SMC, yeah, it's even smaller, maybe 7,000 light years across. And a bit further out, around 200,000 light years distance. So galactic neighbors, yes, but the distances are still, astronomical.
Got it. And how close do they look to each other in the sky? Like if you're looking up.
Visually, they appear about 20 degrees apart.
Mm-hmm.
That's roughly maybe the width of your hand stretched out at arm's length.
Okay.
But in actual space, they're separated by something like 75,000 light years.
Mm-hmm.
So there's a fair bit of space between them, even though they're clearly linked.
Linked, right. And you mentioned neighbors. Are they our closest galactic neighbors?
Well, they're very noticeable, but actually, no. The Sagittarius dwarf elliptical galaxy and the Canis Major dwarf galaxy are technically closer to the Milky Way.
Ah, okay. Now, this I found really interesting. They might be smaller, but they punch above their weight, don't they? Something about dark matter halos?
Oh, absolutely. It's believed both the LMC and the SMC are wrapped in these massive halos of dark matter. In fact, the LMC, it might actually be the fourth most massive galaxy in our whole local group.
Fourth. Out of how many?
Over 50 known galaxies in the local group. So yeah, these aren't just tiny satellites. The LMC is a pretty major player gravitationally.
Wow. So they're actively pulling on us and we're pulling on them, this gravitational dance.
Exactly. It's a constant interaction. Tidal forces are at play, stretching and distorting things. You can even see evidence of the Magellanic Cloud's pull on the outer disk of our own Milky Way. It's warped.
Which leads to this really cool question from the source. Are they bound to us, like orbiting us long term? Or is this more like a first date, maybe leading to a merger down the line?
That is one of the key questions astronomers are wrestling with. One idea is, yes, they're in a very, very long orbit. I mean, 4 billion years or
Right.
even more per loop.
4 billion years.
Right. Or the other possibility is that this is actually their first close pass near the Milky Way, a first approach, as the paper calls it.
And if it is a first approach,
Well, then we could be watching the very early stages of a future galactic merger. It might even happen around the same time, cosmically speaking, as the predicted collision between the Milky Way and Andromeda.
so those faint clouds could be part of a massive future cosmic pileup.
It's a distinct possibility billions of years from now, but yeah, the seeds could be sown right now.
Fascinating. Now, visually, the LMC isn't just a blob, right?
Hmm.
It has structure.
Yes, definitely. If you look at radio images mapping out neutral hydrogen gas, you see a clear spiral structure within the LMC. It's quite distinct.
Hydrogen gas, not visible light.
Well, visible too, but the gas maps really show the underlying structure clearly. And there's more streams of this neutral gas connect both clouds to the Milky Way. That's called the Magellanic Stream.
Okay.
And there's also a bridge of gas and stars connecting the LMC and SMC themselves, the Magellanic Bridge. It's all evidence of this strong interaction.
And chemically, they're different too, compared to the Milky Way.
That's right. They are what we call gas-rich. So a higher percentage of hydrogen and helium compared to our galaxy. And they're also more metal-poor.
Metal poor.
In astronomy, metals are basically any element heavier than hydrogen and helium. So fewer metals suggest maybe they haven't had as many generations of stars forming and exploding, enriching the gas as the Milky Way has. Or perhaps they formed in a less enriched part of the universe initially.
But they are forming stars now. They aren't dead galaxies.
Oh no, far from it. Both the LMC and SMC host active star-forming regions, nebulae, stellar nurseries, and they contain a huge range of stars, some incredibly young, some very, very old. Tells us they've had a long, ongoing history of making stars.
Okay, let's shift slightly. The source really emphasizes the historical challenge of just figuring out how far away the LMC is. Why was that so tough, and why did it matter so much?
Right, the LMC distance. It was, and still is, a cornerstone for the entire cosmic distance ladder. Think of it like the first crucial rung.
The distance ladder.
Yeah, it's how we measure distances across the universe. We measure the distance to something relatively close, like the LMC, very accurately. Then we find specific types of stars in the LMC standard candles, whose true brightness we know.
Like Sahide variables.
Exactly. Cepheids are a classic example. By comparing their known brightness to how bright they appear from Earth, we calculate the LMC's distance. Once we have that distance nailed down, we can find those same standard candles in more distant galaxies and measure their distances, and so on, step by step.
So if that first LMC rung is wobbly,
The whole ladder is unreliable. It affects our calculation of distances to faraway galaxies, and ultimately our measurement of the Hubble constant, the expansion rate of the universe. So getting the LMC distance right was and is a really big deal.
why couldn't they just use parallax, like we do for nearby stars, seeing how they shift against the background as Earth orbits the sun?
Just too far away. The shift, the parallax angle, is incredibly tiny for stars in the LMC. The source mentions it's about 20 microarc seconds.
Microarcsecs, that sounds minuscule.
It is. For comparison, the Hipparcos satellite, which was a major mission back in the 90s for measuring parallax, its precision limit was about 50 times larger than that. It simply couldn't measure such tiny angles accurately.
And even if the angles weren't that small, the clouds are crowded places, right? Hard to pick out individual stars.
Exactly. Hipparcos also had limits on how faint a star it could observe, maybe 11th or 12th magnitude. And it struggled in very crowded fields. The detectors couldn't easily separate light from multiple stars close together.
So how many LMC stars does Hipparcos actually manage to measure?
Very few that met all the criteria. The source says only 36 stars in the LMC and just 11 in the SMC. And even those measurements weren't super precise. Accuracy is around 1.5 to 2 milliarc seconds. Not nearly good enough for a solid distance determination.
So before Gaia, it really was this shaky distance ladder the paper talks about, relying on different methods, different star types, hoping they all kind of agreed.
Pretty much. Astronomers used a collection of techniques. Young stars like Cepheids, older stars like RR Lyrae found in globular clusters, red clump stars, even observations of the cooling sequence of white dwarfs, and the famous supernova SN 1987A, which exploded in the LMC.
Wow, a real mix.
Yeah, each method had its own strengths, weaknesses, and uncertainties. You tried to combine them to get a consensus distance, but there were always nagging discrepancies and debates about the true value. The error bars were significant.
Okay, enter Gaia. The paper calls it a spectacular step change. What made Gaia so different?
Gaia was just a revolution. Launched about 20 years after Hipparcos, its technology was vastly superior. We're talking about the early data release 3, EDR3, which came out in late 2020, based on almost 3 years of data.
And what could it measure?
Astrometry positions, parallaxes, and crucially, proper motions. That's the stars moving across the sky. Gaia EDR3 improved proper motion accuracy by a factor of 2 over earlier Gaia releases. And its photometry measuring brightness and different color filters was also way better.
So much better precision, seeing fainter stars, measuring movement. But the source notes the clouds are still tough targets, even for Gaia.
That's true. They are still pushing the limits of Gaia's accuracy simply because they're so far away. But the key difference was the sheer number of stars Gaia observed and the unprecedented accuracy for those millions of stars.
Millions.
Millions upon millions. This completely changed the game for understanding the structure and the kinematics, how things are moving within the clouds. Lurie et al.'s 2021 paper, mentioned in our source, really showed this paradigm shift.
Okay, so you have this flood of data from Gaia. How do you even start? How do you pick out the actual LMC and SMC stars from all the Milky Way stars in the foreground?
That's the critical first step. You need to filter the data. You look at a star's position on the sky, obviously, but then you use its measured parallax. Even a tiny Gaia parallax gives you some distance information, and very importantly, its proper motion.
How does proper motion help?
Stars belonging to the LMC or SMC will generally be moving together through space in a way that's different from the foreground stars in our own galaxy, which have their own different patterns of motion. So you look for stars that share a common motion characteristic of the LMC or SMC.
Like finding a flock of birds flying in formation against a background of randomly flying birds.
Exactly like that. It allows you to filter out the contamination from our own galaxy and isolate the cloud members.
And once you have that clean sample, you look at their colors.
Precisely. Gaia measures brightness in several different color bands very accurately. Plotting brightness against color gives you a color magnitude diagram, like an HR diagram, but for a whole population. This helps you sort stars by their type, temperature, and evolutionary stage, basically by age.
The numbers are just staggering. The source says initially over 27 million Gaia objects were checked for the LMC area, 4 million for the SMC.
Right, huge initial searches. But after applying those parallax and proper motion filters to ensure membership, they confirmed over 11 million LMC stars and over 1.7 million SMC stars.
11 million.
Yeah.
And 1.7 million. That's just incredible detail.
It's an unbelievable data set. It allows us to map these galaxies star by star in a way that was simply impossible before.
So with this detail and using those color magnitude diagrams, you can really start to dissect the stellar populations, right? See different generations of stars.
Absolutely. For the first time, really, in an external galaxy with this kind of clarity,
Mm.
we can separate out different age groups. Very young stars, less than 50 million years old. Young stars, maybe 50 to 400 million years. Intermediate age stars, up to 1 or 2 billion years old.
Wow.
And we can also study the evolved stars, much better red giants, asymptotic giant branch stars, the pulsating RR Lyrae and Cepheid variables, our standard candles, red clump stars. Each group tells a different part of the galaxy's story.
So what does this level of detail tell us about how the LMC and SMC are actually put together and how they're moving internally? It must be like going from a blurry photo to HD video.
That's a great analogy. One of the huge breakthroughs is separating the ordered motion, like overall rotation, from the random chaotic motion of individual stars, and doing this for different types and ages of stars within the galaxy disk.
Something we could only really do well within our own Milky Way before.
Pretty much, yeah. Now we can examine the structure and motion in the central regions, the bar, the disk, for both clouds in detail.
The LMC is called a prototype barred Magellanic spiral. What does that mean, and how does the SMC fit in?
It means it's kind of the classic example of this type of galaxy. It has a prominent bar-shaped structure of stars across its center, which is slightly off-center, and one main spiral arm. The prevailing idea is that these features, especially the bar and its offset nature, are largely due to the gravitational tug-of-war with the smaller SMC.
So the interaction shapes the LMC.
Very likely, yes. These tidal interactions can pull stars and gas around, creating structures like bars and spiral arms.
And with all this Gaia data, we should be able to build much better 3D models of them soon. See how they're tilted and oriented.
That's definitely the hope and expectation. The sheer amount of kinematic data, how the stars are moving in 3D combined with their positions, should allow for much more sophisticated modeling to figure out their true shapes, orientations, and refine their distances even further.
Are there already hints of this in the current data?
Oh, yes.
Yeah.
Even the initial maps of stellar density from Gaia show cool stuff, like younger stars in the LMC's bar and spiral arm are clumped together more tightly than the older disk stars, which are more spread out. It's like you're seeing the recent star formation hotspots overlaid on the older structure.
Highlighting the active regions, what about the overall motion? Does the LMC rotate like a typical spiral?
Yes. The smooth, proper motion maps from Gaia show a clear, ordered rotation pattern for the LMC disk. Interestingly, younger stars seem to rotate slightly faster than older stars.
And the SMC?
The SMC looks more chaotic. Its internal motions are less organized, more jumbled. This probably reflects the stronger tidal disruption it's experiencing from the more massive LMC. It's being pulled apart more effectively.
Which brings us back to the Magellanic Bridge, that connection between them. How has Gaia helped us understand that?
The bridge is basically gas and stars being ripped out of the SMC by the LMC's gravity. Gaia lets us trace this flow much more clearly. Lurie et al. Used samples of young stars and red clump stars, which are good tracers, to map the density and the velocity of stars moving along the bridge from the SMC towards the LMC.
So we can actually see the stars flowing across.
We can see the stellar component of that flow, yes. And it looks like the bridge isn't just a straight path.
Oh, how so?
The Gaia data suggests that it might actually wrap around the LMC somewhat, maybe connecting with that young spiral arm structure on the LMC's southern side. It points to a really complex dynamic interaction.
And Gaia is revealing other faint features too, tidal arms and things.
Exactly. There are hints, or clear detections now, of tidal arms extending from the LMC north and south arms, which are further signs of gravitational stretching. And there seems to be a density enhancement, a clump of stars, north of the SMC as well. All pieces of this ongoing gravitational puzzle.
It's just amazing how much detail has emerged. And the source mentions more Gaia data is coming.
Yes, definitely. Gaia Data Release 3 was huge, but it wasn't the final one. Subsequent releases were planned, incorporating even more data gathered over a longer time baseline. That means even better parallaxes, even better proper motions.
So even more discoveries about these neighbors are likely on the way.
Absolutely. We'll get even deeper insights into their star formation histories, their internal dynamics, their 3D structure, and their ultimate fate. It's a really exciting time for studying the Magellanic Clouds.
So wrapping this up, we've gone from seeing these as just faint, fuzzy patches in the southern sky, maybe known from explorers' tales, to understanding them as complex, interacting galaxies in their own right.
And the leap in understanding, really driven by Gaia, is just phenomenal, moving from shaky estimates based on a few types of stars to precise measurements for millions of individual stars. It's completely changed the picture.
It really makes you appreciate the scale of things out there and how dynamic the universe is, even in our own galactic neighborhood. These interactions playing out over millions and billions of years.
And seeing it unfold, thanks to tools like Gaia, it's remarkable. These naked eye neighbors still held so many secrets.
And maybe a final thought for you, the listener. Think about what studying these interacting galaxies, our nearest large neighbors, can tell us about our own Milky Way. Does their dance hint at our galaxy's own past collisions or its future merger with Andromeda? What other connections are waiting to be discovered out there? The more we look, it seems, the more intricate and fascinating the cosmos becomes.